Hi everyone, very good evening and welcome back to Geeks for Geeks practice. Please give me a +1 in the chat, guys. If my voice is clearly audible to everyone and everything is working fine, then I will share my screen and we'll discuss the problem of the day for yesterday, that was topological sort. So let me quickly add my screen, okay, and then we can start off. So guys, you can hit the like button and give me a +1 if everything is working fine, so you can interact in the chat. So the problem for yesterday was topological sort, right? So basically, topological sort is an algorithm. You can solve it using various ways. You can solve it using BFS and DFS both. So in this video, I'll be discussing the solution for the topological sort using the Kahan's algorithm, that is the breadth first search approach. Okay. So basically, what is topological sort, right? So in general, let's say if I'll talk about a general scenario. So what happens in colleges is, if you know this, right? So let's say if you have to learn something like, let's say you have to learn DS, right? So there will be a dependency that in order to learn DSA, first of all, you need to know about a programming language, right? That is what you need to know, right? Similarly, if you want to learn about a programming language, so maybe there can be a dependency that first of all you should know about the fundamentals of computer like RAM, ROM, and everything, very basic things, right? So this is what dependency means. And whenever there is a dependency graph, right? So whenever there is a kind of an arrow going from this to this, then there is a dependency that is generated, right? So let's say if you go to SBI like SBI, let's say you go to SBI, right? So in that case, they will send you, you'll go to the counter number 2, then they will send you to counter number 6 and something like that. So there is dependency involved. So whenever we have to solve the dependency based graphs, then we use the topological sort, right? So this is what its use case is. You can solve the alien dictionary problem and many other problems if you want to know more about it, right? But is this much part clear? I hope that it is clear. Now, for solving this problem, we will be using the Kahan's algorithm, right? We'll be using the Kahan's algorithm for solving this problem. So basically, in the Kahan's algorithm, what we do is we use the breadth first search technique for solving the topological sort. Okay. So suppose that we have been given the a particular graph. Okay. So let us say that we have been given this particular graph. Let's say we have been given the second graph. Okay. And it looks something like this. Let's say we have 5. Okay. We have 0 also. Then we have what? We have 4 as well. And we have 1 here. And after that, we have 3 here. Okay. And we have 2 here. And let us do the let us connect the arrows. So 5 is having an arrow towards this and this. Okay, 4 is having an arrow towards 0, then 4 is having an arrow towards 1, then after that 1 is having an arrow towards 3, and 2 is having an arrow towards 3, right? So in this particular case, we have to return the topological sort. So topological sort can be of many ways, right? So in this case, what we can do is, let's say if we had 1 and then we had 2 and 3, right? So in order to do the task 3, we have to do the task 1, and in order to do the task 2, we also have to do the task 1. So maybe we can do 1, then the dependencies are removed, then you can either do 3 or you can do 2 and then 3, or you could have done it like 1, 3 and 2. So there can be many orders of the topological sort. That is also another thing that we need to realize, right? Now when we are using the Kahan's algorithm, so there is one thing that is known as the in degree of a particular node and the out degree of a particular node. So the number of nodes, number of arrows that are going from a particular node is the out degree, right? So if I'll consider the out degree of A, so it will be 3, because 3 arrows are going from A, right? Now if there is a particular node, let's say there is a node B, and let's say 4 arrows are coming towards it, right? So in that case, you can say that in degree of B is 4, right? This is one thing. Now whenever the in degree becomes 0, so we push it inside the final answer, right? We push that particular node inside the final answer. So initially what we will do is we'll iterate through the adjacency list, and we will check the in degree of every node, right? So if you take the in degree of 0, so it is nothing but what? In degree of 0 is 2. You can see here, if you iterate through the adjacency list, so 5 is having an arrow towards 0 and 4 is having an arrow towards 0, so the in degree of 0 is 2, right? Similarly, if you check, so the in degree of 1 is what? In degree of 1 is 1, right? If you check for the in degree of, let's say, something like 2, so the in degree of 2 is also 1, because one arrow is coming towards it. Then the in degree of 3 is what? In degree of 3 is nothing but 2, because 2 arrows are coming towards it. Then in degree of 4 is what? In degree of 4 is nothing but 0, I think, because it does not have any arrow coming towards it, right? Then the in degree of 5 is what? In degree of 5 is also 0. So this means that 5 is not dependent on any task, right? So you can see here, like, there is no arrow coming towards 5. So you can either do the task 4 or 5, right? That totally depends on you. After this part, what we will do is we will simply make a queue for ourselves, right? So what we will do here is we will simply, first of all, we'll make a queue. So let me make a queue for ourselves, right? So we will use the BFS approach and we will make a queue. Now in the queue, whenever the in degree of a particular node becomes 0, then we'll insert that. So initially we'll iterate and we can see that 4 and 5 have the in degree as 0. So I will insert 4 inside the queue and I'll insert 5 inside the queue, and we have a final answer list, right? That will contain the final list of all the elements, right? That will be the topological sorted order, and it can be of many ways, right? Now what we will do is, first of all, we'll take out the front guy from the queue. So we'll start with the BFS algorithm, right? Now we will take out this guy 4, that is the front guy. So I will take this guy out, I will put it inside my answer, and since this 4 is being taken out, so we can say that if this guy 4 is being taken out, so basically this means that 4 is being done. So if 4 is done, so this means all the people who were dependent on 4, their in degree would reduce by 1. So since in the adjacency list of 4 you are having 0 and you are having 1, so you can say that if 4 is getting done now, so these arrows will also get removed. So indirectly we can say that what will happen here is in degree of 0 will reduce by 1 and in degree of 1 will reduce by 1. So in degree of 0 will become 1 and the in degree of 1 will become 0. So whenever the in degree of any child becomes whenever the in degree of any of the connections becomes 0, then we insert it. So in degree of 1 becomes 0, so we insert 1 inside the queue. Okay. After that, what we do is we again iterate. So now the next node, like next element at the front of the queue is nothing but 5. So I will take out 5 here, right? So I take out 5, I push it inside the final list, final answer, and then once 5 is done, right? So the in degree of all the nodes that are connected to 5, they need to be reduced by 1, because 5 is getting done. So this means the 5 was making some people dependent on it, so that dependency is getting removed, so they will decrease. So in this case, zeros and twos in degree will reduce by 1. So you can say that zeros in degree will reduce by 1, so it will become 0. So since it becomes 0, so I will push it inside the queue. Okay. Since zeros in degree becomes 0, right? Then after that, if you will see, right, so I'll also have to remove the reduce the in degree of 2, so it also gets reduced and it becomes 0, right? So I will also insert 2 inside. Now after that, I'll take the current guy. So current guy is 1, right? So I can say that I'll put 1 inside the final answer, and since 1 was connected to 3, so I can say that if 1 is getting done, so it will this arrow will be removed from 1 to 3. So you can say that 3's in degree would reduce by 1. Okay. So in this case, what will happen? 3's in degree gets reduced by 1. So we can simply say that in this case, 3's in degree will become now 1. Okay. Now after that, what we will do is we will simply keep on iterating through the BFS queue, and we have the next node as 0. So we check, does 0 have any arrow going towards anybody? No, it doesn't have. So we can simply say that we will simply insert 0 inside our list, and since there is no connection for 0, right, there was nobody in the adjacency list of 0, so we can simply say that we can simply move forward. So we'll pull it out of the queue, and then the next is in the line is 2. Okay. So now we take out 2, right? So we have 2 here. Now we will say that we will remove 2 from the queue, and now since we are removing 2, so this arrow will get removed. So basically 3's in degree will reduce by 1 and it will become 0. So I'll insert 3 here, right? Then after that, you can say that since 2 is also done, so the front of the queue is having 3. So we'll take out 3 here, and we have 3 here, right? So now we'll check if there is anybody connected to 3. No. So in this case, we can say that we have the final task done. Okay. And all the nodes are done. So we can simply say that we have reached the final state, and we can say 4, 5, 1, 0, 2, and 3. Okay, this is the topological sort that we have got. There can be many topological sorts also, multiple topological sort answers, but this is the one that we have got. So we have got 4, 5, 1, 0, and we have got 2, and after that we have got 3. Right, guys? So is this much part clear to everyone? I think this is the answer for this one. I'm not sure. So 5, 4 is also fine. Then 2, okay. So they have taken it as a different way, but this is also fine. Okay, there can be many answers for it. Is this much part clear to everyone? If this much part is clear, then please hit the like button and give me a +1 in the chat, guys. Is it clear to all of you, guys? Up till now, everyone is clear. If you're clear, then please hit the like button and give me a +1 in the chat. Okay, guys. So I hope that this much point is clear to everybody, right? Now, in this case, how do we solve this problem? So for solving this particular problem, what we need to do is, first of all, we'll create an int degree array, right? So let's say int in degree. Okay, we'll declare an int degree array. And what we will do is we'll declare the size as v+1 because there are going to be v nodes, so v+1. And initially we are going to initialize all of them with 0, right? That is what we are going to do. And then what we will do is we need to iterate through the adjacency list to calculate the int degree, right? So we'll say that int I starts from 0, I is lesser than v, and then we will do an I++ here, right? And once we are doing that, so we will say that the int degree of adjacency of I and 1 plus plus, because because if like if we have a particular node, let's say what I can do is give me a second. So what we will do is we'll iterate through the adjacency list of all the nodes. So let's say j starts from 0, j is lesser than adjacency of I dot size, right? So we'll iterate through the adjacency list of the ith node, okay, and we'll do a j plus plus right here. And right after that, what we need to do is we will simply say that the connection will be what. So the connection, let's say int connection will be what. So the connection will be equal to adjacency of ij, right? So in that case, we need to increase the in degree of this, right? So we'll say that in degree of this connection plus plus, right? Because if let's say in the adjacency list of 1 we are having 2 3 4 something like that, so we need to increase their in degree by 1. So that is what I'm doing here. Once this part is done, so we need to also declare a queue, right? Screen is not clear. Are you sure that my screen is not clear? Because I think that my internet connection is fine. Is it still not clear? I can see that it is clear, Ghansham. Okay, so you can just check with your internet connectivity. So int q. Okay, so I'll declare a queue. Now what I will do is I'll iterate through all the nodes, and I think the nodes are 0 based index, right? Yeah. So just give me a second. So I'll iterate through all the nodes. I starts from 0. I is lesser than let's say v, and then I will do an I++. Okay, and what I will do is if the in degree, like let's say if the in degree of a particular ith node, if it's 0, then I will initially insert it inside the queue. So I'll say that okay, queue dot push this particular ith node, right? That is what we are going to do. And we also need a list that can return the final answer. So we can say that vector int answer, this will be the list that will be finally returning, okay, using the Kahan's algorithm. So what we will do is now we will start with the BFS. So while it happens that the queue size, right, while it happens that the queue size is greater than 0, thank you Amit sir, he's also there with us. So while the queue size is greater than 0, right, while the queue is having some elements, till that point of time we'll keep on iterating. And what we are going to do is I'll first of all take out the current node out of the queue. Okay, so the current is going to be what, queue dot front. So first of all I'll take the front node out of the queue. Okay, and then I will pop it out as I have already told you. And once it is popped out, so since that task is done, so I will reduce the in degree of all the connected nodes by 1, right? So in this particular case, what we are going to do is we'll simply say that int let's say j starts from 0, okay, and j is less than adjacency of current dot size. So we'll iterate through the adjacency list of this current node, and whichever node is connected to this particular current node, their in degrees would reduce by 1 because the current task is getting done, right? So in this case, we'll say that we'll simply do what, we'll simply say that in degree of the connection. So let me declare the connection. So the connection will be what, adjacency of current j, right? So we'll simply do what, we'll simply say that in degree of the connection, okay, we will reduce it by 1. So we'll reduce it, and then we need to check that if the in degree of the particular node, right, if the in degree of the connection, right, if it becomes 0, so this means that it becomes independent, right? It is not dependent on anyone. So whenever the in degree becomes 0, that is when we push it inside the queue. So we'll simply say that we need to we can simply say that we can push it inside the queue. So we'll push this connection inside the queue, and once this part has been done, right, so it will keep on moving forward, right? Because whenever the in degree becomes 0, so it will be pushed inside the queue, and one by one we will keep on taking the front until it is empty, right? And then in this case, you have to return find and return any topological sorting graph, right? So in this case, what we will do is after this part, we can simply return our answer. Let us try and do this and see what the compiler says about this particular sample test case. I think it will work on the samples. Also, one more thing, we need to do what we need to do, answer dot push back the current node. Okay, so we need to push back inside the inside the answer, we need to push back the current node. So we'll push it also. And just give me a second. It says that in degree was not declared, so I need to change the variable name somewhere. Where do I need to change it? Yeah, in degree was not declared here correctly, right? Okay, now let us try and run it and see what happens here. It works on the samples. And if the, like, do I need to return any -1 answer specifically? Let me check. So I don't think that we need to return anything. If you return the topological sort is correct, then console will return 1, otherwise 0. Okay, let's try and test this and see if there is any error that we have made. Okay, it successfully gets accepted, right? So is this part clear to everyone? Right, you can see that it successfully got submitted, because whenever I return the list, so it will check if it is a valid answer, then it will always do what? It will always return 1, and in that case it will be correct. Otherwise, if it is if my answer, if the list that I've written, it is not one of the correct list, then it will return false. So my code will get wrong. So this is how we are doing this particular problem. Basically, if you will talk about the time complexity of the approach that I have discussed, right? So basically the time complexity is what we are just running the BFS algorithm. So you know that the time complexity of the BFS algorithm is order of V plus E. And which algorithm that we use? We use the Kahan's algorithm, right? Use the Kahan's algorithm for solving this particular problem. And if you want to do some problems based on this, then there is a problem named as like courses, there is a problem named as prerequisite courses or courses, right? If you will search courses, and then after that you will write topological sort, then you will get the problem on GFG, right? And then there's another problem that is known as alien dictionary. So it has been asked in a lot of companies, right? So you can try to do that problem also. I've explained it some time back, like I think couple of months back on GFG itself. So you can try to do the courses part 1, part 2, right? There are several problems. There are right, part 1, part 2 is there. And alien dictionary also, it is a hard problem which has been asked in Google. So these all problems are based on the dependency. So whenever you will see the dependency thing, right, then you can understand that you have to use the Kahan's algorithm. Is this part clear to everyone? You have to use the topological sort approach. So that is why you have to use the Kahan's algorithm. Talking about the space complexity of my code, so it will be what? Order of V, because I'm storing V nodes by using the in degree array, right? That is what I'm doing. So you can have a look and let me know if something is not clear, right? So first of all, what I have done is, again, summarizing the code. So first of all, I have declared the in degree of all the nodes as 0. Then I iterate through all the nodes, and I iterate through the adjacency list of all the nodes, okay, and whatever connections they are having, so their in degree will increase by 1. Then I have a queue, and initially whichever nodes are having the in degree as 0, they will be pushed inside the queue. Then I have a final list answer, which will be the topological sort that I'll be returning. And initially I'll check that if the queue is not empty, so the BFS will keep on running. And in this case, I'll take out the current node, and I'll pop it out of the queue. After that, we'll insert it inside the answer. And after this is done, so what we will do is we'll get the connection, and we'll reduce the in degree of the connection by 1, because since that the current task is getting done, so the dependency is getting reduced. So in degree of the connections will reduce by 1. And if there are connections whose in degree becomes 0, so we can simply push it inside the queue, and one by one our answer will keep on getting updated, right, with the current task. And we can simply return it. If it is correct, then the compiler will give us a correct answer. Otherwise, the compiler will give us a wrong answer. So we can check according to that. And the time complexity, as I said, is nothing but the time complexity of the BFS, that is order of V plus E, and the space complexity is order of V. So is this part clear to everyone, guys? Please tell me. Now I'm going to open the GFG ID so that I can give you the code link as well. I hope that this problem was quite easy for all of you and you have understood it. Also, make sure to try out the courses part 1 and part 2 problem by using the topological sort. And also you can prerequisite courses, the problem name is that. And you can also try out the alien dictionary problem. Okay, so I'm sharing the link of this problem. I think it was an easy problem, that is why the attendance is pretty much low today. But is it clear to all of you guys? Just let me know by hitting the like button if everyone is clear with this. All right. So that's very great. I hope that you have understood this problem, right? It was a quite easy problem. It was not that difficult. And it is the base of many of the problems, right? Whenever you see something like dependency, and you can see that there's a direct or cyclic graph that is going to be there, right? Whenever you see that it is kind of a graph, right? Indirectly, you have to build the graph, and there is directed graph, and it is acyclic, so it is not having any cycle. Then you can use it, right? So this was it for today's problem of the day, guys. Thanks a lot for joining, Rishit, and thank you, Ahmad sir, as well. Thank you, everyone. And make sure to keep coding. Make sure to solve today's problem of the day as well. I think Abhinav will be taking the session tomorrow, 12 a.m. in the morning. So make sure to attend it. With that being said, thank you, everyone. And if you have understood it, make sure to hit the like button and give a +1 in the chat. Thank you. And make sure to subscribe the channel as well. Keep coding, guys. Thank you, everyone.